I'm going to talk about the random greedy algorithm for producing a maximal independent set and how to analyze it using local limits. And this is based on joint work with Michael Krivlevich, Tamas Mezaros, and Clara Shicheman. So let me start by a toy example. Suppose we have a circular parking lot and cars arrive at the parking lot one at a time and park at arbitrary locations. And assume that the parking is discrete, namely each park occupies 2 consecutive curbstones. And cars cannot overlap, they really have to find an available slot. And, and they keep coming until no more room is left. And the question is, how many cars will park at the end of this process? And the answer clearly determines on the particular choices the cars have made regarding where to park. So instead of asking about the worst case scenario or the best case scenario, I will ask about the typical scenario, namely when the cars have made uniform random choices about where to park. So we will be able to shortly answer this question, but just before that, let me phrase it in graph theoretic terms. What we are really asking is what is the typical size of a maximal independent set which was produced in a random greedy fashion. So here are some definitions. An independent set is a set of vertices in a graph, no two of which are adjacent. Finding maximum independent sets is very interesting, but also very hard, NP-hard and even hard to approximate. But finding maximal independent sets with respect to inclusion is very easy. How easy? Well, we can apply the greedy approach, namely, given an arbitrary ordering of the vertices, we consider the vertices one by one according to this order and add them to our set or color them red if the resulting set does not span an edge. So 1 will be in our set, 2 will not be, 3 will be, and so on. So this always yields a maximal independent set, but how large will it be? Well, this clearly depends on the ordering of the vertices. So here's an extreme example. If we think of the star and the root of the star is the first vertex we consider, then it will end up in our independent set. Hence, none of the leaves will be there, and the maximal independent set we obtain will be very small. If, on the other hand, we consider a leaf as the first vertex, then the root will not be in the independent set. Hence, all leaves will be there, and the maximal independent set will be maximum with respect to size. So which situation is more typical? Well, at least if the star is large and the first vertex we consider is chosen uniformly at random, then the situation to the right is much more probable. Hence, it does make sense to replace arbitrary ordering by random ordering or uniform random ordering. But given such an ordering, the algorithms are just the same. We consider the vertices one by one, adding them to our set as long as the resulting set does not span an edge. I just mentioned that the obtained sets, the red set here, is just the first color in a random greedy coloring of the graph, which colors every vertex according to the ordering, the first available color. Let us denote by I this set, and by iota its density, its ratio. We call it the greedy independence ratio, and note that this is a random variable, even if the base graph is deterministic, just because of the random ordering of the vertices. And people have been studying this quantity, this random variable, for at least 8 years now. Perhaps started by Flory, who was an American chemistry Nobelist, and later by Page, who is a British computer scientist, who studied it for the line and showed that asymptotically it converges to this number here. And later on, combinatorialists have studied it for various random graph models, McDermott for the binomial random graph with linear edge density, Wormald for the random regular graph, and later extended it with Lauer for deterministic irregular graphs with the exploding Earth. And quite recently, 2 distinct groups, Brightwell, Jansson, and Luchak, and independently Bermol and Youngher and Moyal studied it for a uniformly chosen random graph with the given degree sequence. Before discussing our contribution, let me just give yet another formulation of the same model, equivalent formulation. So given an arbitrary or random ordering of the vertices, instead of considering the vertices sequentially, we may compute a maximum independent set in parallel as follows. At time 0, we suppose every vertex is active, and at each round, every active vertex look at its active neighborhood and see whether it has the lowest label, in which case we call it a sink, and it colors itself red. If, on the other hand, it has a red neighbor, it deactivates itself. And now we go to the next round. Now 8 is a sink because it has the lowest label among its active neighborhood, so we color it red. Quite recently, Fisher and Weaver showed that this algorithm terminates in at most logarithmic number of rounds on each graph, and that this is tight. So in this sense, this algorithm is also efficient. But note that we did have one global step here, that of determining the ordering of the vertices, but we could have easily avoided it if we want a random ordering. Instead, we could have let each vertex choose its own label, just pick a number between 0 and 1 uniformly at random, and this induces a uniform random permutation on the vertices, so the algorithm works just the same. And now you can see that this algorithm is very local in what sense? In the sense that, for example, in order to determine whether this guy here is red, we did not need to read at all the value here. And to determine whether this guy is red or not, we did not need to read the value here. So we only need to look at local neighborhoods, perhaps small, perhaps big, in order to determine the value. And the advantage is that we can apply this algorithm for infinite graphs. Well, not always, because, for example, on the bi-infinite path, if by chance we sample the monotone increasing path sequence, then there are no sinks and the algorithm will not run. But this will never happen. So here's a more typical situation. And now suppose I want to determine the value at this vertex here. I don't need to read infinitely many values. I have to read only finitely many. So how many? I have to read labels on vertices which are obtainable by a monotone decreasing path, plus boundary vertices, just to know that the monotone decreasing path has ended. And now to determine whether this guy here is red or not, I perform the greedy algorithm on this sequence here with these labels. So these guys are going to be sinks. These are neighbors of sinks. This is a sink, and this is a neighbor of sinks. So it didn't end up red. But why would I want to perform this algorithm on infinite graphs? Well, I hope that this will be motivated in my next slide where I describe the general framework. We are given a graph sequence with order tending to infinity, and we wish to calculate the asymptotics of these random variables, of these random greedy independence ratios. So we start by estimating the means of these random variables, observing that the mean is just the probability that a uniformly selected vertex ends up red. And we hope that this will be determined by small neighborhoods, because then we will get some kind of decay of correlation, which will give us that these random variables are very well concentrated about their mean. And we had to analyze this local neighborhood of a typical vertex, which is captured by a very nice notion of a local limit, or Benjaminish round limit, which is typically a random rooted infinite graph. And we reduce our question to determining what is the probability that the root is red in this object, in this limiting object. As a final step, at least in some cases, we are able to develop a machinery to calculate this probability, the probability that the root is red. Okay, so let me now formally define what local convergence means in this sense. We say that the graph sequence converges locally to a random rooted infinite object if for every fixed radius, the ball of radius r around a uniformly selected vertex converges in distribution to the ball of radius r around the root in the limit. So really what this means is that for every fixed ball, the probability of seeing it around the typical vertex in the graph sequence converges to the probability of seeing it around the root in the limit. So this is really convergence in L1 of the probability mass function. Here's an example. Let us consider the sequence of cycles. So for every fixed radius, if we take the cycle to be long enough, then from any vertex at radius r, we don't see the cycle closes. So in that sense, we see a path that goes r in both directions. Hence, the limit will be just a bi-infinite path. Put it somewhere. It need not be deterministic, though. For example, just a couple of examples. The binomial random graph, this is an easy fact, converges locally to a Galton-Watson Poisson tree. And the sequence of uniform random labeled trees converges locally to a size-biased version of this Galton-Watson Poisson tree, which I will define quickly later. But even if the graph sequence is deterministic, non-random, the local limit may be random just because of the choice of the root in the graph sequence, which is random. Okay, so here's our result. We assume that our graph sequence has subfactorial path growth, which is just a very weak assumption on the growth. It's strictly weaker than a bounded degree assumption. Why? Because bounded degree graphs have exponential path growth. The number of paths which emerge from a typical vertex is at most exponential. So this is a strictly weaker assumption. And under this assumption, our theorem states the following. if a graph sequence converges locally, then the sequence of greedy independence ratios, these random variables, converges to the probability that the root is read in this local limit, which I denote by iota of euro. So this is really two theorems coupled together. One theorem is about the means of these random variables, which converge to this number here. And the second theorem is about concentrations of this random variable about their mean. And here we don't really need local convergence, but just the growth assumption. And this was observed by Gamarnik and Goldberg roughly 10 years ago, but for the bounded degree setting. So we extend it for strictly weaker assumptions, but also provide a different proof, which is based on some kind of quite general exploration algorithm lemma, which states more or less the following. We want to determine the value of some Boolean function, say on two distinct points in our graph. And we know that the value of the function determines on a random local neighborhoods of these points. So if we know that the radius of these neighborhoods is typically much smaller than the distance between these points, then we know that the value of the function at these points will be highly uncorrelated. And that will give us the concentration. Okay, so we have reduced our problem to calculate the probability that the root is read in some random rooted infinite object. But this might be very difficult, and even for the two-dimensional lattice, it is widely open for at least 60 years now. Like, no one knows what is the probability that the origin, say, is going to end up read in a random greedy coloring of the two-dimensional lattice. Really, the problem here is the existence of cycles. So instead, we will focus on locally tree-like graph sequences, namely graph sequences for which the limit is almost surely a tree. And with trees, the situation is much simpler, because the root of a tree is going to be read if and only if none of its children is going to be read. Now, if these children are roots to independent subtrees, meaning either they are deterministic trees or maybe they are random but independent of each other, then conditioning on the label of the root, if we only look at the children of the past, children with label which is less than the label of the root, then they will be roots to independent subprocesses. That is, the entire picture I will see here will be independent of the entire picture I see here. Say. And if the laws of all of these subtrees and the main tree are the same law, we call it a single type branching process, and this will give us an easy recursion. And if they have several laws, we call it a multi-type branching process, and then we can still say some things. So here's the recursion for a single type branching process. Let y of x denote the probability that the root is read and that its label is less than x. So we're really after y of 1. This is just the probability the root is read. We can write it as the following integral and take a derivative. So the derivative of y at x will just be the probability that the root is read, given that its label is exactly x. But this will give us the following recursion. This probability is just the average over the number of the children of the past, the number of children with label as an x, times the probability that each of them needs to be not read, conditioning of being in the past, which is what's written here. And this is independently because of what we said earlier, hence the product here. And the boundary conditions y of 0 equals 0 is just by the definition of y. For a multi-type branching process, we just have to add types. And it doesn't make things much more complicated, but it does replace the ordinary differential equation by a system of ordinary differential equations. So size is just the number of types. Okay, so it's not that complicated. So here's an example that I solved the question, at least asymptotically, from the first slide. The paths and the cycles converge locally to the bi-infinite path, and we can think of it as a two-type branching process. One type is of the root type, say, and one type is branch type, and the root type has two branch type children, and the branch type has one branch type child. Now, for a branch type child to be read, it needs its only child, which is branch type, not to be both read and in the past, and we can solve this. And for a root type vertex, we need its two children, which are both of branch type, not to be independently, not to be read and in the past. And we can solve this as well. Plugging in x equals 1, we get the result of Lorentz page. And we actually get a bit more because we get this time evolution thing. If I want to ask what is the situation at time 1/2, like if I ignore vertices with label above 1x, then I get this density. This is just a little bit below the real independence ratio of paths and cycles. An easy fact is that binomial random graphs converge to the Poisson D-branching process if the average decay is D, and then a one-line calculation gives us the result of McDiarmid about the gradient independence ratio of these graphs, and plus the time evolution bonus. And this is, at least when D is large, half optimal, and this is not coincidence. It was mentioned in Gamarnik's talk, I think, that Rahman and Virag showed that these kind of local algorithms are at most half optimal for large D. So in this sense, these greedy algorithms are as good as it gets. A very nice result of GREEMAT shows that a sequence of uniform random trees converges locally to the following size-biased Galton-Watson Poisson 1 tree, which can be defined as follows. We first put an infinite line, and then on each vertex we grow an independent Galton-Watson Poisson 1 tree, which is almost surely finite. So the ball of radius r around a typical vertex in a random tree converges in distribution to the ball of radius r around the root of this limiting object. And this is really a two-type branching process, one type for the spine and one type for the trees. So we can do this recursion. For the tree-type vertices, we've already done it in the 2 slides ago. And for a spine vertex to be read, it needs its only spine child not to be read and in the past, and it needs to be read as the root of a Galton-Watson Poisson 1 tree. This is very easy calculation. Plugging in 1, we get 1/2, which is just below the real independence ratio, which was calculated by Meir and Moon in the 70s. And the simulations that I've made assure that this is really correct, and simulations don't lie, we trust them. But of course I do, because I carefully chose this simulation. But the point is, it is really well concentrated even for this small number of vertices, 250 vertices and about 125 red vertices. Okay, so let me sum up our results. We have the result of Florian Page, we have the result of McDiarmid for binomial random graphs, the result of Wormald for random regular graphs. Here we have a neat probability generating function trick which allows us to kind of skip the calculation of the ordinary differential equations that we obtain. And observing that the local limit of deregular graphs with exploding girth is just the same as for random regular graphs, it's just a regular tree, we have this result as well. And we have a new result about random trees, which can be applied for random functional digraphs as well, one-out graphs. Just as a final remark, recall that the greedy independence ratio of the path converges to this number here, which is just below 1/2, and the greedy independence ratio of the star converges to 1 because I typically start by a leaf. Are these lower and upper bounds? This clearly is an upper bound, and we want to show that this is a lower bound in the sense that if we color or take a greedy independence set in any tree on L vertices, then it will be an expectation at least as large as that in the path. So this was what we wanted to show. Instead, we showed the non-asymptotic result, an exact result, meaning that for every fixed number of vertices, the expected size of the greedy independence set on the tree will be at least as large as that on the path on the same number of vertices. So the tools are going to be very much different and more combinatorial in spirit. Okay, so I'll end by a couple of open questions. What are we doing if we have cycles in the limit? So this is widely open. There are some bounds in some cases, but no one knows how to handle this. It is interesting to analyze some other local rules, other than just pick a uniform random vertex at each step, say. And we can analyze the size of the second color or of the third color, but when we say something smart about it, for example, is it true that the union of the first two colors in the path will be the smallest among all trees on the same number of vertices? We know it is not true for 3 colors because 3 colors just color the entire path, but maybe for 2 colors it is still true. And thank you for listening.
Thank you very much. So let us thank the speaker. There is a question in the chat.
Second order result. Okay, so we have concentration. Are you asking about error bounds?
Central limits here.
No.
One more
it's
question.
easy to compute the size of a maximum independent set. No. Yeah, that's difficult.
Well, I I don't really have questions, but maybe a quick comment. I think the work probably could extend naturally to the partition function, like the physicists call the hardcore model, where you weight the independent sets according to the size of the independent set, and then count the sum of the total weights of the independent set. There is already results on the correlation decay of according to how big the weight has to be, what they call fugacity parameter, and the threshold is exactly known, at least for regular tree, I think. So the local limit would be just a irregular tree, and when the fugacity is smaller than that threshold, which covers your special case where fugacity equals 1. So,
but I think that it's a different model, really, because our independent sets are not uniform maximal dependent sets. They are not uniformly chosen. They are greedily chosen.
No, I'm just talking about, oh, wait. Oh, it's greedy algorithm.
Right.
But I guess
it does not give the uniform distribution unless the graph is transitive.
But I feel that because over there you do know the correlation decay with, I think with the local limit, it should be possible to also prove like the some limit of the partition function or log of the partition function.
So what work is it? Do you remember the names?
I think probably Tristan Saleh may have some results like that, but I don't know if he was exactly working on. I think he worked on the independent set. Yeah, so Weitz was the first one who started this work with this correlation decay thing.
Yeah, that I remember. He had this kind of self-avoiding trees, right?
Yeah, with that technique to deal with the cycles, I think. Yeah.